All right, so first thing we're going to learn about here, new stuff, is that aldehydes and ketones, they're always undergoing this equilibrium called a tautomerization. And this is this very fancy way of saying that there's this internal rearrangement that occurs. Okay, so let's just take a ketone. All right, if we look at one of these carbons next door to our carbonyl carbon, these are what are called alpha carbons here. The one removed from our ketone group, from our carbonyl carbon. The next one's over. These are called beta carbons. If there were more, they'd be gamma, et cetera, right? So this sort of Greek alphabet numbering system indicates how far these carbons are from that carbonyl carbon. So again, alpha carbons are the next door neighbors to our carbonyl carbons. Okay, if we look at these alpha carbons, we're going to go ahead and explicitly put in the hydrogens on one of these. How many hydrogens are there on that alpha carbon? 2. So we got 2 of them sticking off here. And of course, we don't really explicitly write it, but we know that they're there because carbon needs to have 4 bonds. Okay, so this is my ketone. These are in equilibrium with what's called an enol. All right, let's pick apart that word real quick. All, what suffix do we use all for? OL. For alcohols, all right? And what about ene? What does the ene mean? When do we use enes? As in alkenes. Double bonds, exactly. So these are going to be molecules that have a double bond and an alcohol group. And they're going to be right next to each other. That's what makes an enol an enol. Okay? So again, I don't lose any carbons, right? This is this equilibrium. Same number of carbons, same number of oxygens, everything in the same place. Except for now, I have an alcohol group and a double bond with that alpha carbon. All right, and again, we called this thing our alpha carbon here. In my enol, how many hydrogens are on that alpha carbon?
1.
Just 1, right? Because it's got a double bond now, right? So my alpha carbon used to have 2 hydrogens on the left-hand side. Now there's only 1 on the right-hand side, okay? But none of my atoms were lost here. That hydrogen is now located on that oxygen as my alcohol group. So the formula for both of these compounds is the same. C5H, what is it? 6, 7, 8, 9, 10. C5H10O. Right? Same molecular formula. I didn't lose any atoms. I've just rearranged how they are within the molecule itself. Okay, so again, this has this fancy name, a tautomerization, which is just this internal rearrangement that occurs within the molecule itself. All ketones are constantly undergoing this internal rearrangement. There's this equilibrium occurring. And for the vast majority of them, it greatly favors that ketone side. Okay, so if we took a sample of ketone or aldehyde, it's constantly interconverting in this reaction here. But if you froze time and went ahead and counted, the vast majority would be in that ketone form. Okay, it's only a small population that you ever find in this enol form right here. Okay, nonetheless, as far as like a numbers game go, again, it's like it's only a very small population. But nonetheless, this is going to be really important to the chemistry of these molecules, the fact that they're constantly undergoing these sort of internal rearrangements. Okay, so first of all, first thing we need to be able to do is, given the structure of a ketone, I want everybody to take a second and draw me the structure of the enol that it is in equilibrium with. All right, so again, we called these carbons right next door to my carbonyl carbon, the alpha carbon. And it doesn't matter which one you picked. You could have picked one on either side. But importantly, that's where your new double bond is going to be, between your carbonyl carbon and your alpha carbon. All right, so what I'm going to do is I'm going to start, I got to have the same number of carbons and oxygens in both. So I'm just going to start by drawing my ring, put that oxygen on there. Okay, but again, now I have a double bond between what used to be my carbonyl carbon and my alpha carbon, and that hydrogen is now on that oxygen. All right, so there's my enol.
Does it matter if you placed it upwards or downwards since they're both?
No, yes, that's, no. Either alpha carbon would work. These are equivalent. Okay, so looking at this equilibrium again, seeing these explicit hydrogens that we drew, we can see that the whole sort of name of the game here when we're doing our tautomerization is that this hydrogen right here is moving, right? It goes from being on this alpha carbon to now being on that oxygen, right? So that's what's happening in this internal rearrangement, is this hydrogen right here is moving. And that is really, really going to be important to the chemistry of this molecule here. It turns out that these alpha carbons, they're hydrogens. These things are relatively acidic. Okay? So, what does that mean? Carbons are, it's like notoriously difficult to remove a hydrogen from a carbon. Those are pretty strong bonds. It's not something that you can do fairly easily. Unlike, say, removing a hydrogen from an acidic molecule like HCl. That thing will get rid of its hydrogen like that. No effort required. It's giving it away, right? But to pull a hydrogen off of a carbon, it takes a lot of work, okay? It turns out that these alpha hydrogens, though, compared to all other carbon-hydrogen bonds, these things are relatively easy to remove, right? What we would call acidic. Remember, acids are things that donate protons. Okay, so in general, very difficult to remove a carbon from a hydrogen, other way around, to remove a hydrogen from a carbon unless it's an alpha carbon. These things are apparently pretty easy to do. Okay, so out of all the carbons and hydrogens in the world, it turns out that these alpha carbons, their hydrogens are relatively acidic. You can get rid of them pretty easily. All right, and that's going to be really important to the chemistry. So first of all, let's just do that real quick. So let's just do that exact same example again. Boom. Here's my ketone. It's got these alpha hydrogens. Okay, if I have a base coming along, we'll just use the classic base here, a hydroxide. Again, that base is going to be able to steal that proton, pluck it right off of there. All right? Importantly, that pair of electrons that used to be in that carbon-hydrogen bond will still be there, right? When you're things that are acidic, they lose protons or hydrogen ions, not the electrons as well. So if we have a base here, this thing is going to come along and pull that off, leaving me with a carbanion. All right, so I have that negative charge on that carbon. It still has one of those hydrogens on there. I'll draw that in just to be clear. But it lost the other one, and now there's a pair of electrons on that carbon. Okay? This is what we call an enolate. ATE because it's an ion. Okay? And what makes these enolates relatively stable, what makes those hydrogens relatively easy to remove, is this charge can be stabilized through resonance here. So now I'm going to draw these resonance structures. This pair of electrons can come down here, and this pair of electrons comes up here. All right, so these two structures right here in resonance with one another, these are both what we consider the enolate ion. Okay, that negative charge on that carbon can be stabilized because it can sort of spread itself out across these bonds here. It has these resonance structures. If you remember from your previous chemistry class talking about resonance structures are sort of weird. We kind of think about the electrons as switching back and forth, but really both of these structures are true at the same time. It's not so much that the electrons are moving in this concerted fashion, but rather they kind of spread themselves out between these two bonds. They're in both of these places at once, and that's what makes these resonance structures nice and stable. All right, so a base can come along and remove that alpha hydrogen, right? So a base removes that alpha hydrogen, and then we see that that negative charge is stabilized through resonance. All right, so again, you guys gave me the enol of cyclohexanone. Now I want you to draw me the enolate ion in its resonance stabilized form. So both of those structures there for this particular ketone. All right, so the first thing I'm going to do is just put a negative charge, a lone pair, and a negative charge on that alpha carbon. That's my first structure. All right, but these are in resonance. So I'll draw my two-headed arrow here. With then the thing that where the name really comes from, the enolates. So now I'm going to redraw my 6 carbons, but now I'm going to have a double bond between that alpha carbon and what used to be the carbonyl carbon. And now my oxygen is the one with the negative charge. All right, these are the 2 resonance structures of my enolate ion. What's up?
In our homework, is it going to ask us to put the lone pairs and the negative charge?
You will definitely have to put the negative charge. I don't know about the lone pairs. All right, but just note, a carbanion ion, when carbon has a negative charge, it necessarily has a lone pair. And oxygen, as we've discussed a bunch, when it's neutral, it has 2 lone pairs. When it has a negative charge, it has 3 lone pairs. Okay? If we look at our 2 structures of our enolate ion, this one would be considered more stable because the oxygen is the one with the negative charge. Oxygen has its full octet. Oxygen's more electronegative as well, so it's a little bit happier having that negative charge. But this one right here is going to be the one that's more important to the chemistry of these molecules. All right, so where are we going with this? This brings us to our last type of reaction, and we're going to introduce it today and then spend a bit of time on it next class as well because they're kind of tricky. These are what are called aldol addition or condensation reactions. All right, and these are reactions that are going to occur between neighboring aldehyde or ketone molecules. Okay, so I'm going to take a simple ketone here. We'll use acetone, the only one that we refer to by its common name. Okay, and these reactions would occur like if I had a beaker of acetone, what I would do is I would add a little bit of base to it, something like NaOH, and neighboring acetone molecules would react with one another, okay, to form what's called an aldol. Okay, and the name, aldol sort of comes from aldehyde, but this works for ketones as well. All right, so our goal is to try to pick apart this reaction and sort of understand what the heck's going on here. Again, this is occurring between neighboring acetone molecules. So on my reactant side, I'm going to go ahead and put down 2 acetone molecules so we can try to tell what's happening on both sides here. All right. So again, this reaction is occurring between 2 of these guys. So step one, do I have the same number of carbons on both sides of my reaction here, right? Standard sort of operating procedure. I should have the same number of carbons on the left as I do on the right. And I have 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 6. All right, so check, check. I got the same number of carbons on both sides here. I've just joined these two acetone molecules together. All right. Now, let's figure out where our new bond in this structure is. And I kind of have given us a big hint just by coloring things the way that I did. We can see that my new bond here, this is the new bond in this molecule. Right? That was the bond that was formed in this reaction. All right? So, in my purple molecule, which carbon is reacting? What do we call this one here? We got a very special name for this carbon at the base of that oxygen double bond. Carbonyl carbon. So let's just note that my new bond is between my carbonyl carbon in my purple molecule. And what about in my blue molecule? Which carbon? We also have a special name for this one now that we just learned today. The alpha carbon, yep. So in these molecules, we have the alpha carbon of one ketone reacting with the carbonyl carbon of its neighbor. Okay? And not unlike our Grignard reactions that we did at the very beginning, what happens to that carbonyl oxygen? It becomes an alcohol group, right? Just like we saw over here. Our carbonyl carbon gets reacted, and that oxygen becomes an alcohol group. We see the same thing in these aldol addition reactions, right? That carbon that used to have that carbon-oxygen double bond now just has a carbon-oxygen single bond. Okay? So, obviously, these are big, ugly products that we get here. All right. So again, we're going to spend sort of 2 lectures picking these apart, but this is our goal here, is to understand, to be able to draw products for these reactions, as well as to work backwards. If we're given a product of an aldol addition, we got to figure out what 2 ketones or aldehydes reacted with one another. All right. One thing that we can sort of do that is going to be very helpful here is in helping us identify our new bond. Notice how my product has these 2 functional groups in it. Has both an alcohol group, but also that carbonyl group. All right? And a signature of these reactions is these 2 functional groups will always have the same spacing associated with them. All right? If I go and I zoom in here and I start counting from my carbonyl carbon to my alcohol group, they are always going to be located 1, 2, 3 carbons apart. And that new bond will always be between carbons 2 and 3. All right, so new bond between carbons 2 and 3. All right. Let's start trying to break these things apart. Figure out what, we'll start by working backwards here. So I'm going to put down whoa. right? And I want everybody to take a minute and try to identify where my new bond in this molecule is. All right, and again, we're going to count from our carbonyl carbon to our alcohol carbon. So 1, 2, 3. And again, where's that new bond? New bond is between, oops, carbons 2 and 3. So this is my new bond. Okay, so that means this set of 4 carbons here is one chunk. The other set, 1, 2, 3, 4, are my other aldehyde in this case. Right, and they're identical. In this case, I just took a beaker of butanal, added some base to it, and neighboring molecules reacted with one another. Right, so these would be my purple and my blue carbons. Right, so if we just keep in mind that we can always identify our new bonds using this counting method here, we can sort of figure out how to break this molecule apart into its original 2 components. All right, again, if we start counting from the carbonyl carbon towards our alcohol carbon, they're going to be located 3 carbons apart, and that new bond will be between carbons 2 and 3. All right, so I'm going to put down 2 more products here, and you guys tell me what reactants you would use to create these.
would we count?
You have to start from the, if you're going to use the between 2 and 3 rule, you have to start with the carbonyl carbon. All right, so let me try to sort of represent this visually a little bit differently. Okay, so I'm going to start from my carbonyl carbon and start counting 1, 2, 3, right? And that trick helps me easily identify where my new bond is. All right, so if I want my reactants that created this new bond, I'm just going to work backwards. I'm going to erase that bond there. Right? So that means that this was one chunk. This was the other one. But of course, in my reactants, it didn't start out as an alcohol group. It started out as a carbonyl group. So I'm going to have to draw a double bond and get rid of that hydrogen. Right? Once we identify our new bond, we just break it into those two parts. That's how we figure out our reactants. So same name of the game here. I'm going to identify my new bond by counting from my carbonyl carbon over to my alcohol carbon. All right, that means that that new bond is right in the middle there. So if I go ahead and break that, I get my one chunk here. All right, but in my reactant side, this wasn't an alcohol group, but rather a carbonyl group. So I'm just going to draw that double bond, get rid of that oxygen. All right, and in these cases, these were symmetric, so my two reactants were the same. All right, that doesn't necessarily have to be the case, so everybody take a second and give me my two aldehydes or ketones from the following. So I'm going to start counting from my carbonyl carbon to that alcohol carbon, because again, that helps me identify my new bond. Okay, so then to get my reactants, I'm just going to break that bond. Oops, it's a little aggressive. Okay, that gives me my first ketone very easily. Okay, and then remember for my other fragment here, it didn't start out as an alcohol, but rather as, in this case, an aldehyde. So I'm going to draw that double bond and get rid of that hydrogen. So these are my two, an aldehyde and a ketone that reacted with one another to produce my aldol, right? That's what we call this thing on the other side. This is my aldol. All right, so we learned how to work backwards. Next class, we'll sort of work on putting these together to get our product. We'll sort of pick up where we left off here and add a little bit more to it next time. But this is going to be our last reaction that we learn for this particular chapter. Actually,